Okay, so I just want to show you one more thing, which is a position representation of the time evolution operator. Okay, and before I do that, let me discuss the time evolution operator a little bit more. Okay, so let me postpone this to something a little bit below, and before I do that, let me just discuss a property of the time evolution operator. Because you might say, is it a Hermitian operator? So this operator has this weird form, e to the power minus I by h bar, h of t. Now see that if I have, say, h squared, and I take its Hermitian conjugate, then I get h squared. Why is that? Because Hermitian conjugation, I've not proved this, but you can show this, it reverses the order of the operator, okay? So AB, the Hermitian conjugation of AB is Hermitian conjugation of B, Hermitian conjugation of A. Now, if I take the Hermitian conjugation of h squared, you know, this is just h dagger, and this is a Hermitian operator, so I get h squared. So any power of a Hermitian operator is just going to give me back that power of Hermitian operator. Okay, so if I take u of t and take its Hermitian conjugate, what I get, and you can show this easily, is that I get e to the plus I by h bar, h of t, okay? Here there was a minus sign, okay? And here there's a plus sign. So what we find is that the u dagger operator has this minus plus sign. So if I multiply u of t with u dagger of t, I get 1. And it doesn't matter which order I do this. Okay, so I should probably be consistent and put the dagger here. Okay, so such operation, so that means that u dagger of t is inverse of u. Okay, it's the inverse of u. Such operators are called unitary operators. Okay, and given a Hermitian operator A, any Hermitian operator, you can construct a unitary operator in this way. So let me just give you the recipe. And this is also something that is very useful in group theory. So, you know, you should definitely hang on to this fact. Suppose I give you a Hermitian matrix or an operator. Let's call it, say, M. M is some Hermitian operator matrix. So it satisfies this. And if alpha is a real parameter, then if you take the exponential of I times alpha times M, then U is going to be a unitary operator. Okay. So every Hermitian operator gives rise to a unitary operator through this construction. This has far-reaching consequence in quantum field theory, in quantum physics. Okay? We shall see that all observables in nature, if it is conserved in time, it's automatically related to a symmetry. And that symmetry is that the evolution under that symmetry operation is done by that unitary operator. Okay, so this is something we will see in the future. It's related to something called Noether's theorem. Okay, so let me now give you a position representation of the time evolution operator. So we want to discuss, in physics, we are interested in causality, right? That's what the time evolution operator is doing. It is a statement of causality, just telling you that if I know the state of the system, if I know the if I know the state of the system at time t0, we can predict the state at a future time. Future time by using the time evolution operator. Okay, so, but let's go take a step back and think about wave physics. So in wave physics, suppose that you know about, say, Huygens principle, and what Huygens principle said is that suppose you have some time t0, and this was space. So you have a one-dimensional space, so this is x, and you have some wave function defined on that, at that time. Okay, so this is your initial condition. So what you ask from physics is that, what will be the wave function of your system at a future time? So let's call this x prime, and this future time is t, and in the future time, the coordinate is x. So you want to know what this wave function will be at a future time, right? And you know that, from fluid mechanics, from wave mechanics, that if you take, say, a point over here, the value of the wave function here will not only just depend on the wave function at that same value in the past, but it'll depend on all different values, right, to a certain extent. Things will propagate, disturbance will propagate out like this, right? And the value of the wave function here will depend less on this part than this part, but you want to know precisely how this distribution of wave function at time t0, gives rise to a wave function at a future time. Okay? So in other words, you want to know psi, which is a function of x and time, in terms of psi, in terms of its x prime at t0, right? You want to see that this thing depends on x and t, this thing depends on x prime. So that means that, and intuitively you know that, whatever we want, whatever is happening here will, in principle, will depend on all the values of x in the past, because it'll have some time for this part of the system to propagate here. Okay, and in Newtonian physics, it's even more likely, because in Newtonian physics there is no, signals can travel at whatever speed they like, right? There is no upper limit. So that means that in between there must be an integration over x prime. And there should be a function, let me call it u, no, let me call it k. K is the right. K, which will depend on, of course, x and t, as well as x prime and t prime, which we are taking to 0, right? So this function k has a name. In physics, this is called a propagator. Okay? In mathematics, it's called a Green's function. Okay? And what it is actually, in disguise, k is the time evolution operator in disguise. Okay? So this is what I want to show you as our last thing today. So we want to show you that the propagator is the time evolution operator. Okay. So we use Fourier analysis for this. So remember the Fourier theorem, which related psi of x to psi of x prime. It's basically taking the Fourier transform twice, then I get 1 over 2 pi h bar, two integrals with psi of x prime 0, e to the power I by h bar, p x minus x prime d of p d of x prime. So this is the Fourier integral theorem. And we derive this when we are discussing Fourier integrals. Okay. Now, if I apply u onto this thing, yeah, okay. So before I do that, yeah, that's fine, yeah. So u of t, psi of x of 0 is psi of x of t. But here, what we can do is that we can take u inside the bracket, and then what we have is we have an integral over dx prime, and inside we have integral over d of p, and then we have u of t, and then we have ei by h bar p, px minus x prime, and I close the integral, and then I put psi of x prime of 0 of dx prime, right? So this shows that this is the formal expression for k x t x prime 0. Okay. Now I want to evaluate this for the free particle. Okay. For the free particle, okay, so right. So for the free particle, what do we know? We know that psi of, say if psi is an eigenfunction, then psi of x of t is going to be e to the power minus, say p squared by 2m I by h bar t, right? Times psi of e of x of 0. Okay? So now, if I look at this now, then I can use this expression over here, and in terms of u, I get this guy, and I now if I rearrange everything, then there is going to be a Gaussian integral, and once you do the Gaussian integral, you will find that u of t, why am I using u? It should be k. K of x of t, x prime of 0 is m over 2 pi I h bar t to the power half e to the power I m x minus x prime to 2h bar t. Okay, so yeah, I think this is not the cleanest derivation. Let me just make sure that this is something that we have covered in detail in the tutorial, okay? So because I derived it for an energy eigenstate, but you actually don't need to use it for an energy eigenstate, okay? Yeah. Actually, yeah, I can prove it for without the energy eigenstate, because, you know, here I wrote this as e to the power energy, but if I wrote it as e to the power just a Hamiltonian, e to the power, you know, minus I by h bar, the free Hamiltonian times t, and this didn't have to be the energy eigenstate. This can be any general eigenstate. Then once this guy goes inside the integral, you know, these things, yeah, for inside the integral for a free particle, we can kind of, we know how this thing is, what the form of this thing is. This is going to be some has a special form, because we can write the energy eigenstates, the free particle state, as an integral over the energy eigenstates. But I think, you know, this is something. Let me just end it here, and either I will cover it in the next lecture, or I will set the, you know, allow you guys to kind of figure out the details in the next tutorial. Okay. So I just wanted to show you that this has, so this is for the free particle. Okay, this is for the free particle. So in general, you know, finding out the propagator for a interacting system is much more difficult, and you have to use what is known as perturbation theory. Okay, but I just wanted you to kind of know that the time evolution operator has a very concrete form. It's a function. Okay, so let's end here. And do you have any questions?
I'm kind of confused what x prime is in this.
X prime is the coordinate of the particle at a past time. Okay, so, you know, what this guy is telling you, what this thing is doing. Sorry, let me go back to this picture. Okay, what this is telling you is that suppose at some time t, you ask a question about a particular value of x. What is the value of the wave function at this value of x, right? So we know the whole question, the whole point of physics is to be able to predict this value from some boundary condition in the past, right? Right? Now, yeah, since we're dealing with wave phenomena, we know that. So, for example, you've heard of Huygens principle, and what Huygens said is that for if this is a wave front, then every point on this wave front acts as a source of spherical waves, and the wave at a future time is just given by the envelope of those wave fronts, right? So, you know, so for wave mechanics, you know, the value of the wave function here, in principle, will depend on the value of the wave function at all values of x in the past, right? Because, you know, stuff can propagate from here to here. Suppose the particle has a lot of energy, right? So it's traveling fast, so it can travel from here to here, or here to here, here to here, right? So, you know, so you expect the wave function here to depend on all the values of x in the past, and so we have to integrate over those values of x in the past, and that is what x prime. X prime is the integration variable that denotes the wave function. It's the argument of the wave function in the past. Okay.
So
or it
does
acts
it
on the
span?
argument. Sorry. It acts on the argument of the wave function.
So does it span the entire axis? Like, are we integrating over the entire axis?
Yeah, it spans your entire system.
I see.
Yeah, yeah. If your system is finite, then of course the integral will be finite. But yes, in principle it's infinite. Yeah, because if I look at, this is the equation, is this is the here's the propagator, right? So here we are integrating over all x prime. So this is this was done a little bit sketchily, but I will. This is an extremely important, and it turns out that if you want to find this, the propagator is nothing intrinsically quantum mechanical. This is just the general problem of wave physics, right? So Maxwell's equations, if you're looking for, electromagnetic wave solutions, you can say, okay, I see the electromagnetic wave in my detector here, but it must have left Andromeda galaxy 2 million years ago. So, how is the state of the universe 2 million years ago, going to influence what I see now, right? So here, 2 million years ago, this thing is going to be the surface of a sphere surrounding us, whose radius is 2 million light years, right? So, so this is also in electrodynamics. When you solve Maxwell's equation for the wave equation that you can derive from Maxwell's equation, you also have to solve the propagator. And it turns out to actually find the propagator, there's always going to be, you have to solve what is known as a hyperbolic equation. And that always involves doing a contour integral. So contour integrals are actually, if you want to have the general solution to this, contour integrals, will play an important role. Okay, so this is something that I want to put in the tutorial, but it might be a bit too heavy. But you guys, tutorial is for you to have fun, right? So even if I put a bit of heavy stuff, that's okay. The last tutorial was pretty light, so. Okay, any more questions or comments?
I actually have one more question.
Yeah.
With the right moving and the left moving wave, I don't know, I just noticed this, I'm not sure if it's related, but does it have something to do with charge conjugation and time reversal, because you have the conjugate of that, like you have I and minus I, and the sign of the time is different?
Yeah, of course. I mean, it is also that, right? I mean, if you reverse the time, then you change the way that the wave moves. But you see, there is an operator in quantum mechanics, which is the time reversal operator. And what it does is that it reverses, your system's time evolution. It turns out to be a anti-unitary operator. It's an anti-linear operator. So it is not possible to have the time reversal operator to be a linear operator. It has to be an anti-linear operator. And that's one of the few cases in quantum mechanics where you actually have anti-linearity rather than linearity. And that's an interesting problem that maybe one day we can talk about. The operator which actually, so we haven't really talked about how to incorporate charges in quantum mechanics. And I don't think I can do that in this course. But yeah, the charge conjugation will become more clear, that it's related to time reversal when you learn about how charged particles are described in quantum mechanics. Okay, so in charged particles, it turns out that your momentum operator P has to be replaced by P plus some charge times the vector potential, the 3 vector potential. So in the Hamiltonian, for the Schrodinger equation, wherever you had the p operator, will have to be replaced by this operator. But this thing is not. It's a you've seen the vector potential, right?
Yes, I've seen it before.
Yeah, and the vector potential is not a unique object. It has something called the gauge symmetry. So you can change it by the gradient of an arbitrary function. So it turns out that when you make that transformation, the wave function itself will also change up to a factor of something.